Hello, my name is Michael Sliwa, and in today's video we're going to be talking about the following problem on the screen right now, which is for the following reaction, determine which mechanisms are likely to occur. So we have an alkyl halide reacting with an ethoxide in a polar protic solvent, which is going to be the alcohol right there, also known as ethanol. But we are also going to be talking about a second aspect of this problem, which is drawing a reaction coordinate diagram for both of the mechanisms that we talk about on that first slide there. And also, in addition to that, drawing the reactants, products, activation energy, and delta G, and including the structures of the intermediates and transition states in the diagram as well. But we're going to go ahead and start on this first piece right here. As I already started saying, we have an alkyl halide here, and first we have to determine what kind of alkyl halide this is. So if we look at the halogen bromine right here, it is actually going to be secondary. The reason we know this is because it's bonded to two other carbons here and here, which is going to be important when looking at the next part of this problem. So when we're looking here at this ethoxide, we have to think of a few things. The first thing we notice is that it's a good nucleophile. That's because there's a electron pair here that can be used for reactions and, things of that nature. We'll get into that as we draw out these mechanisms. And we also have a good base. And also we know that in both of these, this is a pretty relatively small nucleophile and or base, depending on how it's going to act. And as we know, usually nucleophiles are more important in our SN mechanisms and bases are more important in our E mechanisms. So we can kind of get an idea of how this is going to work out, but we also have to look, since this is a secondary alkyl halide, here at our solvent, which is going to be polar protic, as I mentioned before. The way that I tell that is by looking at the visible H here bonded to the oxygen. And in saying that, we also know that we're going to experience some solvation, which is going to change our good nucleophile and good base into weaker nucleophiles and weaker bases, not so good. Which is going to cause us to form a carbocation intermediate with both of these types of reactions. It's just that the products we're going to be getting are going to be a little bit different, and again, we'll get into that. But as I mentioned before, SN reactions, we're going to be looking at this good nucleophile here, but since we have that good nucleophile being solvated into what we could call a bad nucleophile, we're actually going to have that carbocation intermediate, only one molecule in our rate law, and this is going to be SN1. For that same logic, we could look here, and since we have a carbocation intermediate being formed, this is going to be going by a E1 reaction mechanism. So I'm just going to start down here and go pretty quickly, since this isn't really required, but I think it's good to show in drawing both of these reaction mechanisms. So we're going to start with SN1, and of course, we're just going to have the same reactants as we have above. So just going ahead and drawing those in, and we said that this is polar protic, which is good to know. So the first thing we need to look at, since this is an SN1, is what this alkyl halide is going to be doing. And we know that this leaving group here, Br, which is a good leaving group, is just going to end up leaving. And we know if this was an SN2 mechanism, these electrons off of this negatively charged oxygen would come in here and create a new bond all in one step. But that is not exactly the case because of the solvent that we're working with. So like I said, we're going to be forming a carbocation intermediate, which is going to look a little bit like this, with a positive charge being on the carbon where our bromine ended up leaving in this first step here. So now this is actually where our electrons off of this negatively charged oxygen are going to come in. They're going to go ahead and go to this cation site, or this positively charged site here. What's going to happen is that a new bond is going to form at that carbon with the oxygen. So the negative is going to the positive, basically. So here's our new bond, here's our oxygen, and we still have this ethyl group coming off the oxygen here. This, of course, creates a new functional group on our molecule here, which is going to be an ether. And something else that we have to take into account is how these electrons are actually coming into this positively charged site and ultimately neutralizing it. So it could either come in from the front, since there's no, steric hindrance here. It could either come in from the front or the back. So it could also come in under in the back here. And we could expect to see two different types of stereochemistry, and it's going to be a 50-50 racemic mixture of these two different structures. So the first structure here is going to retain stereochemistry. We're going to see a wedge. And the second structure here is actually going to be an inverse of stereochemistry, which is going to be the dashed line here. And these are still, bonds and everything, but it's just the direction. This one's going back into the page. This one's coming out of the page at us. So that basically covers everything in the SN1 reaction. Now we're going to go ahead and do the other reaction I said, which is E1, which again is going to start the same exact components here. We have bromine, ethoxide with its lone pair of electrons, and also ethanol here, still polar protic, we already know this. And we are still going to form the exact same carbocation intermediate because the bromine is going to leave, leaving us with this structure here. Now, since we're looking at an elimination reaction, things are going to go a little bit differently, and we're more concerned about these carbons here and the hydrogens that are going to be attached to them. So here, we have 2 hydrogens coming off, which is going to be our alpha hydrogens because they're on the carbon that we're kind of looking at here. They are the first position. But then we also have 3 hydrogens coming off of here, which I'm only going to draw 1 in, which would be at a beta carbon or a beta hydrogen right there. And we would also have, 2 hydrogens coming off here. We'll just choose one. We'll go with this one on the right, and that's also going to be a beta hydrogen. Now, we kind of have to determine which one of these hydrogens we're going to want to knock off with this pair of electrons here, which is what's going to be happening in an E1 mechanism in order to create a newly formed double bond, thus making an alkene out of this alkane structure here. And what we're going to want to do is look at which is going to make the more substituted alkene, which ultimately is going to end up being the left side. So the one on the right side would create a less substituted alkene, and this one will create a more substituted alkene, which is lower energy and more stable and more favorable for the reaction. So in drawing that, we go ahead and go into the next step here. What's going to end up happening is that this lone pair of electrons is going to go after this hydrogen here, breaking that bond, causing the hydrogen to leave, and then the electrons from here are going to go into this single bond here and create a double bond. So we're starting with a sigma bond, and now we're going to a sigma bond with a pi bond, which is a double bond. So that's going to go ahead and look a little bit like this here. And that's the product we're going to be forming. The other thing we have to take into account is also stereochemistry, because we are also going to see a molecule that looks a little bit like this. So we're going to go ahead and we're going to have cis isomerism on the same side, and we have trans here on opposite sides, and this is referred to as Z, and this is referred to as E conformations. So in saying that this top one here, this E conformation, is lower energy, this is actually going to be our major product, and the Z conformation here is going to be our minor product because it's not favored. The same goes here if we were to talk about knocking off this beta hydrogen. We would expect to see another minor product that would be very much more unlikely and very much, worse energy-wise than these two. And that would form the alkene on the very, very most distal end of this entire chain. But we really wouldn't see that as much, but it is, kind of important to say that it could be formed as a very minor product. Now, if you notice, in both of the first steps here, our bromine is actually leaving, so we could technically say that here in this step, we have a Br minus in solution, also the same over here. And then if we were given, normally we'd be given like a counter ion like sodium. So the sodium cation would end up actually bonding with this bromine anion, and that would also form this last step here, NaBr, and also over here, NaBr in the last step. But since we aren't given this counter ion, it's not really pertinent for us to show that or say that. So I'm going to kind of go ahead and scribble that out. But that is important to go ahead and realize, if we were actually carrying this reaction out and not just writing it out on paper. With this reaction down here as well, we would still have, this hydrogen that came off in solution as well, this hydrogen cation, which would actually go ahead and bond with our ethoxide here, and then we would also expect to see the product over here of just an ethanol as well. So this is a bit of a mess, and we did go pretty fast, but basically what we're trying to get at here is that an E1 mechanism and an SN1 mechanism, are likely to occur with this specific set of molecules in solution. So now we kind of have to move on to the next step here, which is drawing a reaction coordinate diagram for both of these different reactions. So we're going to start over here with the SN1 mechanism, and of course do our reaction coordinate diagram, so kind of doing the base template here. So on this axis we're going to have reaction progress, and on this axis here we're going to have energy. So before we could do this, I think it's really pertinent to talk about the rate law for the SN1 reaction of this. So we're going to start with rate equals K. And as I said, only one component is included in the rate law, and that is the alkyl halide. So it would look a little bit like this. And I also said that we would form an intermediate, so we know that this SN1 mechanism here is going to be stepwise and going to have some sort of intermediate here. It's also important to note that in SN1 mechanisms, our reactants are actually going to be higher energy than our products. So if we draw on the line here between the parts that we have here, we're going to have one transition state here, go down to our intermediates, second transition state, all the way down to our products. And of course, coming from our reactants up to our first transition state is going to be activation energy. Delta G is going to go from our reactants all the way down to our products here. And that delta G here is going to be negative because we have an exothermic reaction where the products are favored over the reactants and are therefore, lower energy in comparison. As I mentioned before, if we were to label this is our intermediate. And again, transition states are at the top of both of these humps here. So now we kind of have to think about what kind of molecules we're going to be seeing at these different parts here, which can get a little bit tricky, but if we refer back this drawn out mechanism here, it gets a lot easier. So in my opinion, it's a lot easier to start at our products down here and our reactants up here. So I'll go ahead and label this 1. We could draw our reactants, and I'll label this 2 as the products, and we could go ahead and start drawing those. So our reactants are going to include this alkyl halide here, Br, and we are also going to see the reactant of our ethoxide coming in up here as well. And for our products, we're going to see the two structures that I ended up drawing that are a racemic mixture, which are going to look, if I draw them correctly, like this. And those are going to be our two products, along with, we would have our NABR or something to that effect if this reaction actually had a counter ion, but we're not shown that. So I'm not going to show it just for the purpose of that. But, you could potentially have that as well if it is in solution, which it should be. So then now we're going to take a look at our transition states. So that would end up including, so this first transition state, would expect to see the alkyl halide, starting to kind of leave here, and this bond starting to break, which eventually at our intermediate here, which I guess I could go ahead and label 5, would actually end up looking like this with our carbocation. So that's what we're going to be seeing there with bromine off in solution, or actually bromide here because it has a negative charge on it. Then at our second transition state, we're going to start to see a bond forming, kind of forming here with the negative oxygen end of our ethoxide. And as I said, it could go either, from the front through, a front side attack, or through the back through a backside attack, creating these two products. And that's pretty much labeling everything. However, I do think it's important to kind of go in order. The numbering is a little bit messed up here, but first we would have our reactants here. Then we would go to our first transition state where this Br is starting to come off of our alkyl halide here, which is then going to form a carbocation intermediate with bromide kind of floating around in solution. And then at our, second transition state here, we're going to have the formation of a bond begin to happen between the negative oxygen on our ethoxide to this positively charged site here. And then finally forming two different products through front side attack and backside attack. That pretty much sums up everything we need to know here for our SN1 mechanism, and now we can actually go ahead and move on to our E1 mechanism, which is going to look fairly similar but a little bit different, and there are some, differences that we do need to take into account when looking at this type of mechanism as well. So then for our E1 mechanism, we could follow the exact same process here with drawing this energy coordinate diagram where we have reaction progress, or coordinate, you could say either one, but I usually go for progress, and then energy on the other axis here on the y-axis. So as mentioned previously, our rate law is going to only include this alkyl halide, looking at that, because it's E1, unimolecular, which also means that we're going to have an intermediate yet again, and that's what we saw reflected here in our initial reaction mechanism here for the E1. We also had a carbocation intermediate. So then obviously we're going to need to label that. But something interesting about the E1 mechanism is that it's a little bit different as far as energy goes than our SN1 mechanism. So while in our SN1 mechanism we drew the products lower energy than the reactants, it's actually the reverse in an E1 mechanism because we're doing bond forming. And actually our reactants are going to be lower energy than our products, and drawing in that line here, one transition state, down to the intermediate, the transition state, down to the higher energy products. This line is a little bit shaky, but you kind of get the idea. We go from low energy to an intermediate that's a little bit lower, go up again, and then we go down to our products, which are actually higher energy than our initial reactants. Then drawing in things like activation energy, we can see that the activation energy goes from here to here. It's going to be pretty dang high. Transition state, as we said before, intermediate here. And then we're going to have reactants here and products over here. I guess we could go ahead and do that. Starting material, which is reactants, and then products here. In addition to that, we could draw our delta G, which will go from our reactants to products. And this is actually going to be a positive delta G this time because the reactants are going to be favored, which is endothermic. And now we could go ahead and start kind of drawing what things are doing. So I'm actually going to go ahead and go in order this time and label this 1, 2, 3, 4, and then 5 for our products. So starting at our reactants here, we're going to have the same reactants, which is going to be the alkyl halide, and also our ethoxide here. At the first transition state, we're going to have something a little bit different, but honestly, like pretty much the same actually, which is just going to be this bromines bond kind of breaking and that kind of leaving and starting to break that bond. As that happens, we're then going to form our intermediate, which is going to be the carbocation with the positive charge here. And once we hit our fourth transition state, this is where things change a little bit. So we're going to have, this same carbocation kind of structure here. But what's going to start happening is, we have these hydrogen atoms coming off of here. I guess just one we're going to be looking at, where that bond is going to start to break as that hydrogen leaves. And then the electrons from this bond here, let's just say this is 2 lone electrons, are going to start to kind of come here and form this new pi bond, or this new double bond right here. That's kind of what our transition state looks like. Bonds aren't completely formed, but things are kind of starting to move to the positions they should be in. And this positive charge is kind of also, going away. It's not really leaving, it's just kind of being neutralized by this new double bond being formed. This could also look like our other conformations here, depending on what hydrogen we're talking about. So for this one, for our minor products, still have this kind of a structure going on, but this is still going to be kind of forming. This hydrogen here is going to be kind of leaving, and along with that, those electrons are kind of going to be going here, as we said before. So that would be our Z conformation. This is our E conformation, and we still have our positive charge, which would be right over here. And then we could also talk about our other E conformation that's going to be also a minor product, not very much favored, which is going to look like this. So we have this at the distal end here. We have a hydrogen, like here, which with that bond starting to break, those electrons starting to go here. And that's going to form the products that we also talked about. But we also are, kind of leaving something out here, which is this formation of one of our other products, which is going to be this alcohol, this ethanol. And that's going to kind of be happening in between here and here, I believe, kind of in this space, as these hydrogens are like leaving, right? They're going to start being attracted to this O- that we had all the way up here, in solution. And that's going to, of course, form, a hydroxide at the end of here, this ethanol. And this ethoxide really isn't being used up in the reaction. It's kind of being used to move electrons around and, donate electrons, which is what bases usually are going to be doing. They have electrons, and, we're going to have something over here that wants electrons, which is this positive charge. And that's kind of how that's going to form. So I believe that, first, though, of course, these hydrogens have to be detached from this whole chain before this can be formed, which is why it's a product. But these are kind of, a little bit related to each other in that sense. And at the products end, of course, we're just going to have the same products. So like I said, our major product here in the E conformation, then we're also going to have that same kind of product here with the, the alkane or the alkene in the same spot, but it's going to be a Z conformation because they're on the Z same side and have steric interactions, which is why this one's worse than this one, which doesn't really have the same steric interactions. And we're also going to have our least favorable E product, which is going to have this at the distal end, like I said. Really bad because it's not as substituted as these two. And if we were to rank them, this one would be our best. This one here would be our second best. And then this one would be our absolute worst as far as energy goes. So in looking at all our work here, I believe that we've completed the problem. So we drew the following reactions, the SN1 and E1 mechanisms, which are likely to occur with the given molecules in solution. And we kind of talked about that. Then we got into actually drawing the coordinate diagrams for these mechanisms, kind of talking about how energy is different between those two, saying that here products are not, or are going to be favored, they're going to be favored in the SN1, whereas in the E1, they're not going to be favored, and the reactants are going to be favored. And we also drew some of the potential products and, different molecules we'll be seeing at different transition states and things of that nature as well, which we also did for E1. So that's basically the video. These are all the answers, and hopefully you enjoyed.